Hi. Thanks Rahul, and thanks to the organizers of this workshop for asking me to give this talk. So what I'm going to be talking about today is a very simple result. So it's a compression algorithm for AC0 mod P. So I'm going to define these terms to begin with. So I should say that this 45-minute talk has less content than many of the 15-minute talks I've seen. So you should feel free to interrupt and ask me questions and things like that. So what is a compression algorithm? So let me just briefly review something that we've seen quite a few times in this program, especially if you've been in the boot camp. So this is an example of what is called a meta-algorithmic problem. So what is such a problem? So generally an algorithmic problem where the input or the output has something to do with a model of computation, a circuit, a formula, something like this. This is what we think of as a meta-algorithmic problem. So intuitively, understanding efficient algorithms for this problem involves understanding certain computational models. Okay. So examples of these problems are there are quite a few examples, very natural examples. So circuit sat is definitely an example, where your input is some sort of Boolean circuit, and you want to decide whether it's satisfiable or not. Right? Is the function computed by the circuit identically 0? Another example, similar to circuit sat but in the algebraic setting, is the polynomial identity testing question. Again, your input is an algebraic circuit or an arithmetic circuit, and you want to decide if the polynomial computed by the circuit is identically 0 or not. So the problem that we're going to be looking at is slightly different from these and similar to one that Eric was talking about in his talk yesterday. So he talked about the minimum circuit size problem. Here, the input to the problem is not a circuit. The input is the truth table of a function, right? So your Boolean function on n bits. So the truth table of this function is a Boolean string of length 2 to the n, and that's the input. And say you have a size parameter k, that's also part of the input. And the question you want to answer is, does this particular function have a circuit, a Boolean circuit of size at most k? Okay, so that's the minimum circuit size problem. Yeah. So all these problems are really well studied in the literature. There are lots of results about them. So the problem I'm going to be talking about is a slight variant of this, the minimum circuit size problem. You can think of it as a kind of gap version of this problem. Okay. So you have, let's say, a class of circuits that you're interested in. I don't know, it could be AC0 in this. For the result that I'm going to be talking about, we're going to be looking at AC0 with mod P gates. Right? And so the compression problem for this class of circuits was defined in this paper appearing last year. I think all the authors of this paper are actually in the audience. So nice. Okay, pretty good. So anyway, the input to this, again, is a truth table of a function. So you have a 2 to the n bit string. It's the truth table of a function on n bits. Right. And what you're promised, so it's a promise problem, you're promised that this function has a small Boolean circuit from this class. So let's say it has a small AC0 circuit. You know that. Okay. And the problem is, okay, find a small circuit from this class. Well, not necessarily a circuit from this class. Find some small circuit for this. Okay. So given the promise that this function already has a small circuit, construct some other small circuit, right? A non-trivially small circuit. I'll get to what that means in a second. It doesn't necessarily have to be from this class. It could be a general circuit. Okay. In a sense, you're distinguishing functions with small Boolean circuits from this class from random functions, because random functions don't have small circuits. Okay. So what does non-trivially small mean? Yeah. Here, non-trivially small means something that is better than what you expect for a random function. So it's known that most functions don't have any Boolean circuit of size less than roughly 2 to the n by n. And if you can do significantly better, usually we'll be doing, let's say, significantly better than this in the sense that it will be 2 to the n by something that's super polynomial in n. If you can do something like that, then you really can distinguish such functions from random functions. And so that's a non-trivially small circuit. Any questions about the definition? Yeah.
What is just a small circuit?
What is just a small circuit?
Or input. The input is a small Boolean.
So the input is actually a truth table, right? And
the promise is that it has a polynomial.
Right. Okay, right. So yeah, the promise is that it has, let's say, polynomial size circuit. Yeah. So I'll be a little more formal in a second, right? So let's say polynomial size circuits to begin with.
So this is a harder problem than the problem of distinguishing from random.
That's right. This is a harder problem. Okay. And the interest in this problem is that similar to the meta-algorithmic problems we saw on the last slide, this is intimately related to the question of lower bounds. Okay, so like Ryan's result for circuit sat and many other results, so we know that if you can actually come up with compression algorithms for interesting class of circuits, that will imply lower bounds for these class of circuits. your lower bounds in X for.
Is there like some kind of thing that, there is the general notion of relating distinguishing and prediction. So if you can distinguish from random, does it give you some kind of a circuit, maybe at least a non-deterministic circuit or some crazy thing like that?
So distinguish, I mean, this seems intimately related to natural proofs and things like that, but but that's exactly what that's about. So.
Yeah, so if you have even very natural proofs, then you get a circuit lower bound for nx intersect O(n)x.
What I ask is, if you have can sometimes you get an algorithm that solves the easier problem, the problem of distinguishing from random, and make it into a compression algorithm, maybe by using.
Okay, so we put in, yes, so it's not known that any natural property gives you a compression algorithm.
Yes. Even in principle, you could allow like the general circuit to even have like to be non-deterministic circuit or something like that.
Okay.
Yeah, but you could just guess and check it. Right? I mean, you could guess so you can check that it's the right circuit.
Okay. So yeah, I know. All right. So anyway, okay. So this is the interest in, for example, these kinds of compression algorithms. So even solving a very special kind of promise case of the minimum circuit size problem kind of gives you non-trivial lower bounds. Okay. So that's why we're interested in this. All right. So let's just start off. So I just want to kind of build intuition for the results that are already known. Let's start with a very simple case of the compression problem. Yes.
How tight are those lower bounds? Are they as do they have similar quantitative parameters as the circuit stat stuff?
They are similar, yeah. So the proofs are similar to the circuit stat stuff. So I imagine that the parameters are, quite similar. Yeah. So the authors of this paper, feel free to correct me if I'm wrong. Okay. So let's start off with the compression problem for DNFs, right? So it's a very special case of AC0. So just depth 2 circuits. You're writing the circuit is just an OR of terms. Each term is just an AND of literals. Okay. So this is actually a very well-studied problem. So you're given the truth table of a function. You promise that it has a DNF of size S. You want to construct a non-trivially small DNF for F. And this is just the DNF minimization problem that I think is fairly well known. Right? So how does one go about solving this problem? Well, there's a very simple connection to the set cover problem. So you can just use set cover algorithms to actually solve this problem pretty well. So let's just go through that. Okay, so what is this problem? So you're given a Boolean function. So this is my kind of attempt at drawing the hypercube here. This diamond is the hypercube. So you have your Boolean function that splits the hypercube into the 0 inputs and the 1 inputs. Okay? And what you know beforehand, your promise beforehand, is that this Boolean function does have a DNF of size S. So it has a circuit of this form, right? Each of the ANDs in this circuit computes an AND of literals, which is, it accepts a subcube in the hypercube. And therefore, you know that the ones of this function can be written as the union of at most S subcubes. So that's what it looks like, okay? And what you want to do is actually find a small union of subcubes that covers the ones of the function, okay? So pretty straightforwardly, this is actually just a set cover problem, right? So you're given this Boolean function f, you can construct all these subcubes that are contained in the one set of f. So recall that your input size is 2 to the n. So looking at all these subcubes, there may be 3 to the n set subcubes, but that's still a polynomial number in terms of your input size, right? So you just write down all these subcubes and then run maybe, let's say, the greedy algorithm for set cover or something. And there's classical kinds of results that tell you that the greedy algorithm is a good approximation algorithm in the sense that it will output an answer that's at most a log the universe size far from the optimum. Okay? In this case, the universe size is at most 2 to the n, so there's an order n approximation, and you can get this in polynomial time. Okay? So what does this give us? It tells us that if you start with a function f with a DNF of size s, and let's say this s is not too close to 2 to the n, so let's say it's 2 to the n minus t, where this t is large enough so that this becomes significantly smaller than 2 to the n, then this kind of very simple greedy procedure of covering the ones of f with subcubes will give you a DNF for the same f of size roughly 2 to the n minus t again, right? So if you're much smaller than 2 to the n to begin with, you get something that's much smaller than 2 to the n. Okay?
So
right.
In this case, it's just size ns, right?
You're right, it's just size n times s, yeah. So, but essentially the savings remain more or less the same, right? You don't want s to be 2 to the n by n, in which case you don't get anything, right? Yeah. Okay, so already this very simple result can be used in conjunction with kind of strong results from the literature about circuits to obtain non-trivial compression algorithms. Okay, and this is work done by Chen et al. So this is what they observed, is that if you start with a circuit, if you have a result of the following form, now you have a more powerful class of circuits, not necessarily DNFs. If you know that circuits from this class of size S can be converted to DNFs of non-trivially small size, right? Then you can just use this algorithm and obtain a DNF, not just a general circuit, a DNF of non-trivially small size for your function. Okay. And already this works for many simple, many nice, not very simple class of circuits. So for example, AC0, right? So if you look at AC0 circuits of sub-exponential size, so just to recall, an AC0 circuit is a bounded depth circuit. So it's no longer depth 2, but some constant depth. It's made up of AND, OR, and OR gates, and you have literals feeding in at the leaves. So for AC0 circuits of sub-exponential size, it's known that such circuits can be converted to DNFs, right? These DNFs are not very small, but they're still non-trivially small. So they have size 2 to the n minus t for a reasonably large t. Okay, and these are recent results of Impagliazzo, Matthews, Paturi, and Hostad from a few years ago. And so now using these results, you actually know that these circuits have small DNFs, and therefore you can run the DNF algorithm and get a non-trivially small circuit. Okay. So this is the exact bound that's obtained. So I just want to kind of state this because I want to compare it to the bound that's obtained for AC0 with parity gates and mod P gates. So the bound obtained is the following. So you start with an F which is promised to have an AC0 circuit of size S and let's say depth D. Okay. So the algorithm that I talked about kind of obtains a circuit of this for this same function of size 2 to the n by some discount factor capital M, where this capital M is this funny thing. Okay. So it's exponential in n over log s over n to the d minus 1. So it's really precise. Yeah. And what's kind of interesting about this, and something I want to stress, is that the regime in which this algorithm is non-trivial, the regime in which the circuit output is non-trivially small, is exactly the regime in which we have lower bounds for AC0. Right? So the strongest lower bounds we can prove for AC0 are of the form 2 to the n to the 1 over d minus 1. And in roughly this regime, the size of the circuit output is much smaller than 2 to the n by n. Okay, so roughly in the regime where we have lower bounds, we have non-trivial compression algorithms. Okay, so this is a really nice result. And this is actually not very surprising because it goes through the same machinery that we use to prove lower bounds. So this is kind of what Avi was talking about yesterday when he said that every lower bound that we know gives an algorithm. Right? So the lower bounds that we know for AC0 kind of yield this algorithm in particular and other algorithms. And we're going to see that the same thing happens for AC0 with mod 2 gates. Okay. So this is the result for AC0. So it also results for many other circuit classes. So for example, you can talk about De Morgan formulas. So now these are circuits that are not bounded in depth, but they're kind of tree-like. The underlying graph is tree-like. And you're made up of AND, OR, and NOT gates. So for De Morgan formulas of size much smaller than n to the 1.5, you can actually show that these can also be converted to DNFs of small size. Right? And this again follows from kind of classical results of Subotovskaya about random restrictions and their effects on formulas. You actually need slightly stronger versions of these results, and these are due to Rahul and strengthenings due to the authors of the Chen et al. Paper. So you can do this, and therefore you can again convert these into small DNFs, non-trivially small DNFs. You can use the algorithm, come up with a non-trivially small circuit. Okay. So also a bunch of other results about other models of computation that I'm not going to get into in very great detail. So it turns out that you can use further ideas, not just the DNF idea I told you, further ideas based on memoization and things like that, and push these bounds up. For example, this n to the 1.5 can be made n to the 2.5. And there are also results for general formulas, branching programs, and other results. Okay. So, but the focus of the rest of this talk is going to be about this AC0 kind of compression algorithm and whether it can be pushed to slightly stronger constant depth circuit classes. So, any questions about? I think that was it for, yeah.
I guess the general question is how do we know how this thing compares with the set-based approach to prove lower bounds? Is one better than the other? We don't know.
So I don't know of any formal result that says that SAT algorithms imply compression algorithms or vice versa. Though in every case that I know that there is a non-trivial compression algorithm, there is already a non-trivial SAT algorithm. So for example, even the AC0 mod 2 that I'm going to talk about, Ryan also has a SAT algorithm for this circuit class with roughly the same kind of improvements, so to speak.
ACC, I guess, we just have SAT and not.
For ACC, we have SAT but not compression. Yeah.
Is it only closure properties of C for this to give you a low bound, right? While for SAT, we need some kind of, we get it for some slightly larger class.
So that's, what kind of overhead that you have here? Nothing.
Well, I mean, if it's a C compression algorithm,
Yeah.
just get low bounds next against C.
There is like absolutely no overhead. I mean, do you like add 1 to the size of
I think you need a quadratic size blow up, and at least the way the proof is written right now. So I'm not 100% sure that you don't need any overhead. Okay. So any other questions? Okay. All right. So the question that kind of motivates us now is that can we come up with compression algorithms for more powerful class of circuits? Okay. And the circuits we're going to be looking at are just the AC0 circuits that I talked about in the last slide, but you now augment them with the power of some sort of modular computation. Okay. So specifically for the rest of this talk, I'm going to talk about AC0 with mod 2 gates, right? So mod 2 gates are essentially gates that can do some modulo 2. So they're parity gates. They're kind of depicted with this funny 0 plus sign, right? And again, we are sticking in the constant depth regime. And the question is, okay, can we prove similar results here? Okay. And definitely the techniques that I've spoken about so far, conversions to DNFs and so on, don't really work in this setting because even the simple parity function does not have DNF of non-trivially small size. So we need some sort of new techniques to handle this. Okay. Yeah. And so the main result is kind of, just to contrast with the Chen et al. Thing, is that we get similar results for AC0 mod 2. Okay, so suppose I start with a function that's promised to have an AC0 mod 2 circuit of size S. Then we can, in some polynomial in 2 to the n time, find some circuit for the same function of size 2 to the n over m, where this m, again, is non-trivial exactly in the case where we know non-trivial lower bounds of this class. So it's exponential in n over log s to the 2 times t minus 1. So exactly in the regime where we have lower bounds, we get non-trivial compression algorithm. Right? And so it turns out that this result also works for AC0 mod p, where p is any prime. Okay. So right, so I just wanted to kind of state these results formally, but for the rest of the talk, I'll just think of D as some constant. So we look at some constant depth circuit. And let's assume that S is polynomial. So S is n to the order 1, D is a constant. And in that setting, what we really want is a circuit of size 2 to the n over exponential in n over polylog n. Okay, that's the kind of regime that we'll be shooting for. All right. Yeah, and as I said earlier, so the results that go into proving a result of this form are again closely tied to the lower bound results that we know for these circuit classes. And the lower bound results that we know for these circuit classes are very closely related to polynomials. Okay, so let me just briefly review some material about polynomials, and then I'll go to the description of the result. So we're going to be talking about multilinear polynomials over the field F2, right? So we have n variables x1 to xn, which will normally be bits, right? And we're looking at multilinear polynomials that take values in F2, okay? So for example, things like this. So the thing about a multilinear polynomial is that it's a very special case of an AC0 mod 2 circuit, right? So if I have a multilinear polynomial like this, then that's really a depth 2 circuit. It's got a parity gate on top, a mod 2 gate on top, and what are feeding into it are just monomials. So monomials are just ands with variables feeding into them. Okay, so it's a very special kind of depth 2 AC0 circuit. Okay. In particular, if the polynomial has degree d, right? So if all the terms that feed into the mod 2 gate are all degree d, that means each of these ands that we're looking at in this circuit over here involve at most d variables, which means that the size of this circuit is bounded by something like n choose d. It's actually a number of binomial coefficients up to d. Okay, right? And the interesting thing about polynomials and how they relate to AC0 mod 2, other than the fact that they're a special case, is that we know that polynomials can actually be used to approximate arbitrary functions in AC0 mod 2. Okay, so in the sense in which polynomials approximate functions is the following. So I'll say that a polynomial p, epsilon approximates a Boolean function f if it's equal to f on all but an epsilon fraction of the locations. Right? So on a random input, it's equal to f with probability 1 minus epsilon. Okay. Right? So the results we know about polynomials and AC0 mod 2 are the following. So there's a very famous work of Razborov from back in the 1980s where he showed that polynomials of low degree can epsilon approximate an arbitrary AC0 mod 2 circuit. Okay, so just think of this as a non-trivial result in the sense that it says that any AC0 mod 2 circuit, which could be a really large depth, can be squashed down into a depth 2 circuit as long as you're okay with the circuit erring in a few places. Okay, so we might have some arbitrary circuit which is computing, let's say, of polynomial size, which computes some Boolean function. The polynomial will compute a Boolean function that's very close to the Boolean function computed by the circuit. So there will be a few errors. You'll err possibly on the zeros and on the ones just a little bit. But the degree of this polynomial is not very big. Okay, so the degree of this polynomial is only logarithmic in the number of variables, right? As a result of what we saw on the previous slide, right? So if you have a degree d polynomial, the size of the depth 2 circuit you get is only n choose at most d, right? So if you get a polynomial of degree polylog n, then this gives you a circuit, a depth 2 circuit of quasi-polynomial size that kind of approximates your Boolean function. So it's equal to a Boolean function on most of the inputs. Right, so this is what we know about AC0 mod 2 circuits, and the question is, can we leverage this in order to come up with a compression algorithm? Okay. And if I tell you something like this about AC0 mod 2 circuit, this actually leads to. So if I tell you this about general circuits from this class, a very natural kind of approach to the compression problem is the following, right? So I know that I'm given a truth table. I'm promised that it has small circuits from this class. So I know that there's a low degree polynomial approximating my circuit, right? It's equal to my circuit almost everywhere. So what I'll do is I'll try to find this low degree approximation, right? Okay, so I'll find this approximation. I have this approximation with me. Then I know at what points it's erring. Because I have the truth table of the function, I have the polynomial, I can just compare them. I know at what points it's erring, right? The size of this polynomial is not very big. As I said, it's a depth 2 circuit. It's a low degree polynomial. It's not very big. Right? What I can do is kind of just attempt to fix the polynomial at the points where it's erring. Right? So I can start with the polynomial, kind of get my hands on such a polynomial, and once I have this polynomial, I can just try to fix it. I can say, okay, these are the error locations. I kind of brute force and kind of just fix the polynomial at these error locations, and that will give me an overall a circuit of size, the size of polynomial I had to begin with, plus the locations I kind of had to fix. Right? So I had something like epsilon times 2 to the n locations to fix. I'll fix those.
Think of epsilon, say 1 over n to the log n, like because you're just trying to save like a circuit of size 2 to the n over
right.
n to the log n is a good thing for you.
That's a good thing for me, right? So 2 to the n by super polynomial is fine, right? So I can take epsilon to be inverse super polynomial, right? Ultimately, epsilon is going to be close to inverse exponential, but yeah. So for now, just think of epsilon as being just inverse super polynomial 1 over n to the log n or something, right? So this is a very small collection of points, so I just kind of fix the polynomial I get at all these points. So I'll change the polynomial. I'll say, okay, here's a brute force circuit that if the input lies in this error set, the brute force circuit will do it for you. Otherwise, you just delegate the computation to the polynomial will do it for you, and you're fine. Okay, so this is a kind of very natural kind of approach to take. Yeah, and the only problem with this approach is this step 2. Okay, so how do you find this polynomial p? Okay. And it's not clear how to find this polynomial p. So this was the approach suggested by Chen et al. Already. And it's not really clear how to find this polynomial p. Really, this can be stated as a problem of maybe decoding Reed-Muller codes in certain regimes. But the distance parameter you're looking at is really much more than the minimum distance. Okay, so it's kind of decoding in a funny regime of this well-studied Reed-Muller code, but it's a different kind of regime than what people actually look at. But you're promised, you know that there is a code word in this regime, right? But the problem of finding this code word is not entirely clear. Okay. So this is a very natural approach, but it kind of breaks down because it's unclear how to carry out this procedure of actually finding the polynomial. Okay. So our way of kind of fixing this, so before I go on, is this kind of thing clear? I mean, there's, yeah, okay. So our way of kind of circumventing this is to change the notion of polynomial approximation. Okay, we'll change the notion of polynomial approximation. That will blow up the size of the polynomial, but actually it will make the polynomial much easier to find. It will just be the problem of solving a system of linear equations or something. Okay. So what's the different notion of polynomial approximation we're going to use? So we're going to use a kind of one-sided version of polynomial approximation. So let me say that a polynomial, so as opposed to epsilon approximation, let me say that a polynomial is a certifying polynomial, right? It's a certifying polynomial for my function if whenever the polynomial is 1, the function is 1, and that's it. Okay. So the polynomial that I'm thinking about, so this again is my function. So the polynomial that I'm thinking about is going to be 0 on all the zeros of my function, right? and it's going to be 1, therefore possibly only in a small subset of my 1s. So it guarantees me that when the polynomial is 1, the function is 1, but I don't have any guarantees on the error. Okay, so the polynomial, the way I've defined it, in fact, it could be 0 everywhere. So that's a certifying polynomial. Okay. So I'll throw in one additional condition. It's a non-zero polynomial. So I have a non-trivial kind of certificate of being 1. Okay. All right. So the definition of this is clear. Okay. So just a one-sided kind of approximation. So this has been studied actually quite a bit in the literature already. So it's closely related to a real version that was introduced by, as far as I know, by Aspness, Beagle, First, and Rudich in a kind of classical paper in the 90s. So this particular definition was kind of introduced in the name, it was called weak degree when it was introduced by a paper of Fred Green's in the mid-90s. Okay, it's also been studied in the crypto community quite a bit. They call it algebraic immunity. All right. Yeah. So again, so this is similar to our previous notion of approximation, only we get rid of errors. But on the plus side, it's kind of one-sided. We know that when the function is 0, the polynomial is 0. Okay. So it turns out that you can say something about how well these polynomials approximate functions in AC0 mod 2. But in order to understand when such a result is non-trivial, we need to understand what we can say about arbitrary functions. Okay. So any function, it turns out, any function has a certifying polynomial of degree at most n by 2. Okay. So contrast this to the fact that any function can be written as a polynomial of degree at most n. That's an obvious fact, right? But it turns out that any function has a certifying polynomial of degree at most n by 2. Right? So n by 2 is kind of the trivial regime here. Okay. Right? So there's a little bit of a star here. There's a small caveat. You need to assume that the function is kind of balanced, or it has more 1s than 0s in order to make a statement like this. But let's assume that this is true for any function. True for almost any function. Okay. So this is the kind of non-trivial regime. And if you take, for example, this certifying polynomial of degree at most n by 2 and write it down as a circuit like we've been doing, just write it down as a brute force depth 2 circuit, you'll get a kind of local circuit. The local circuit will compute the function correctly here and here, right? But the local circuit will be really big. It will be of size the number of monomials of degree at most n by 2, which is more or less 2 to the n. Okay. All right, so it turns out that if you know now that the function actually has a small AC0 mod 2 circuit, then you can actually improve on this kind of trivial result. Okay. So this is what we know for any function. So in a kind of theorem that we had, result we had a few years ago, so Swastik Koparty and I could show that if a function in fact has an AC0 mod 2 circuit of polynomial size, then you can improve on this n by 2 a little bit. Okay. You can actually get certifying polynomials of degree n by 2 minus n over polylog n. And this minus n over polylog n is kind of crucial, right? Because it's, n by 2 is trivial. It's n by 2 minus something much smaller than n by 2, but that's crucial. That's what makes it non-trivial. Okay. Right? And if you translate this again into a depth 2 circuit, right, you'll get a depth 2 circuit where the size of the circuit is the number of monomials of degree at most n by 2 minus whatever, but that's much smaller than 2 to the n.
So you assume that you don't get just one polynomial like that, but you get many of them that cover the all.
Absolutely, yeah. You're 2 slides ahead of me. Yeah, absolutely, that's what we're going to do ultimately. So these polynomials are going to be our replacements for subcubes from the DNF case. Okay. All right. So okay. So right. So as I said, so if f has an AC0 mod 2 circuit of polynomial size, then you have a non-trivially large and non-trivially small certifying polynomial. Yeah, and the difference between this and the epsilon approximations that we talked about some time ago is that you can actually find these certifying polynomials. Okay, so that's the advantage, right? The kind of computational advantage to using these things. And why is it that you can find these certifying polynomials? Well, it's not really hard to see. It's just solving a system of linear equations. So I want to find a polynomial, say, that is certifying for my function, right? So I know that there's a certifying polynomial of degree at most d. This theorem guarantees me that. So what I want is a function, a polynomial which is 0 here and non-zero here, right? Imagine the process of just writing down this polynomial. So this is what the polynomial is going to look like. So for every monomial of degree at most d, there's a coefficient, right? And now I treat these coefficients as kind of variables that I need to find, that I need to solve for. For each point in the 0 set here, I need the polynomial to be 0 at this point. So that gives me a constraint on these coefficients. I can write down the system of constraints and I can solve. Okay, right. So for each of these, there's a constraint I can solve, and this solution is some sort of vector space, and what I want is a non-zero element of this vector space. Okay. So a priori, note that the number of variables here, the number of variables here, it's something like the number of monomials of degree at most t. Yeah, so it's much smaller than 2 to the n. But the number of constraints here is, let's say the function is balanced, the number of constraints here is like 2 to the n. Okay, so a priori you have like an over-determined system, homogeneous system of linear equations, right? And there's no reason to expect that this has a non-zero solution. But the theorem guarantees you that there is a non-zero solution. Okay, yeah, and we'll see the proof of this theorem. Again, it goes back to the Razborov polynomial approximation. But once you have this theorem, you know that there's a non-trivial solution. You can find this non-trivial solution in polynomial time because you just want to solve a system of linear equations. Okay. So, any questions about this? Yeah.
So, and can you make sure? I guess you can also make sure that it's non-zero on any particular point.
Right, so we'll have to get to that. It's important that it be non-zero on different points when we cover the entire space. Yeah, so that's the kind of thing we just still need to get to. Right.
Into your original circuit. Or
absolutely. Yeah. Yeah, absolutely. So, yeah. Okay, so right, so we have the system of linear equations that we can solve, and so the set of all solutions to this linear equation forms some sort of vector space, right? And it turns out there are non-zero elements in this vector space, and if we pick one of them, that gives us a certifying polynomial. Okay, so again, so now we can find some certifying polynomial, but this is not a circuit that actually computes our whole function, right? It computes our function very locally. It computes it correctly on all the 0 inputs, computes it correctly on some of the 1 inputs. So, but we want to compute it on all the 1 inputs. How do we do this? And the idea again goes back to DNF. So what we're going to do is try to kind of cover the ones of this thing by a bunch of certifying polynomials, right? So what we want to do is find lots of certifying polynomials that kind of cover this entire region. Okay, and if we do this with a small number of certifying polynomials, then we are done. Okay. Okay, so when you try to prove something like this, you will naturally run into some sorts of issues. Yeah, and the reason for this is that what we are doing, the space of solutions we are looking at is defined by a bunch of linear constraints, right? So you have one linear constraint for every point here. And the bad thing about having these constraints is that they can imply other constraints, right? So for example, forcing it to be 0 here and here might force it to be 0 here. And that's not something you want. Because if that happens, then you'll not be able to cover this point with any certifying polynomial. Yeah, so this is one of the problems we need to overcome. And there's one other. So let me just show you a couple of, yeah.
If you have that,
right.
if every point is possible to have zeros and a 1 at this point, then you take a basis, and a random linear combination of basis elements will cover about half the space.
Absolutely, but there may be points that are never covered by any solution.
Okay.
So those are really the problem points. What you're saying is absolutely right. So if there are points which are not kind of forced to 0, so we're going to get to it in a couple of slides anyway, so okay, good. All right. All right. So there are a couple of kind of problems with this approach, and the first and more serious problem is that having all these constraints for points on the left side can force linear combinations here to be 0. So which means that every certifying polynomial that I look at, every certifying polynomial is always going to vanish at these points here. Okay. So I'll call these points a set of forced points, so F for forced. So these are those points on the right hand side among the ones of the function, so that every certifying polynomial actually vanishes at these points. Okay, and these points are really bad because no matter how many of these certifying polynomials I take, I'll never be able to cover these guys. Okay, so we'll need to kind of argue that F is small. Okay, and once we argue that, we'll kind of be able to brute force over F and kind of just fix the circuit at these points. But then there are the other points, okay? There are these points. At these points, it is possible that certifying polynomials are non-zero. So for every point here, there is a certifying polynomial that's non-zero at some. There is some certifying polynomial that's non-zero. But we still need to be able to cover all these points with a few certifying polynomials. Yeah, this is the second kind of thing. And this is what kind of Russell was talking about. And what he was saying was that if you know that there's a point here which is not kind of forced to 0, then you can actually find certifying polynomials that cover all these points kind of quite efficiently. Okay. All right. So anyway, so there are these two issues. So what I'm going to tell you is that the first issue, it turns out, is slightly more serious, and we'll need a kind of literature, some work from the mathematics literature to actually solve this problem. But the second problem is actually very easily circumventable, and you can solve it quite easily. So let me tell you how to handle the second issue first. Okay, so you have some small set of forced points. Assume that this is, we forget about these. Now we need to cover the rest using these certifying polynomials, right? And it's kind of easy. It's just a linear algebraic argument to show that if you take a random certifying polynomial, right, a random polynomial from our space of certifying polynomials, it's going to cover every point here with probability a half. Right? So you just pick a random polynomial. There is a polynomial that's non-zero at some point here, and a random polynomial is going to be non-zero with probability a half. Okay, this is just some simple linear algebra. But once you have something like this, what you can do is just choose a few random polynomials. So you choose one polynomial that covers roughly half the space, another, and pretty soon you're done covering the entire space. Okay? So if you pick something like order n many random polynomials like this, with high probability you're going to have covered the entire space except for these really bad guys. Okay? So you take order n such polynomials, take the OR of these, and that covers everything except for the bad guys, which we still have to show to be small. Okay. So this kind of gives you a randomized algorithm to do what we want, and you can easily de-randomize this algorithm using some simple error correcting codes or something. Okay. So let me just kind of, yeah.
Just 5 minutes.
5 minutes left. Okay. Okay. So let me just kind of summarize our approach before I tell you the main part of the argument, which is okay. So what is the argument, right? So we started off with these Razborov approximations, which are like two-sided error approximations to our Boolean functions. We said that we can't really find these approximations, so using these approximations is not a good idea for the compression algorithm. So now we are looking at one-sided approximations, these certifying polynomial approximations. And we need to argue that there is a small degree certifying polynomial for our function, assuming that it has a small circuit. Okay? But this is just the analysis. But once we have this, right, and we don't just need that there's a small degree certifying polynomial, we also need that the number of forced points, the number of really bad guys, is small. But once we have these two facts, what we do is we kind of just obtain order n polynomials from the space of certifying polynomials that covers all but the really bad points, right? For the really bad points, what we do is we just kind of come up with a brute force DNF that outputs 1 on those really bad points. And putting things together, we get a circuit for the entire thing. Okay? So the size of this circuit is roughly the size of these certifying polynomials. There are not too many of them. There are n of them. So roughly the size of these certifying polynomials plus the size of, plus the number of forced points. And if the number of forced points is really small, then you're done. Okay? So the only thing to do is to kind of argue the first line of this, that this actually happens. Okay? So since I have only about 5 minutes left, I'm probably not going to get through the entire argument, but let me just give you an idea anyway. It's very, very simple. Okay? And again, it goes back to a kind of classical result of Aspness, Beagle, First, and Rudich regarding how to do this. Okay? So just recall, so when we want to construct certifying polynomials for our function, we really want to solve a system of linear equations where the number of variables is far fewer than the number of constraints. Yeah? So it's not a priori clear that a solution exists. But it turns out that using these Razborov polynomial approximations, these two-sided polynomial approximations that we were talking about some time before, you can drastically reduce the number of constraints you need to look at, right? And you can start with a kind of overdetermined system of linear equations and make it a very underdetermined system of linear equations. And definitely then you're guaranteed that a solution exists. Okay? So what's the idea behind this? So more formally, you start with an epsilon approximating these Razborov type polynomial approximations of really low degree, right? So these are really low degree polynomials, but they can err on both sides. So they can err here, they can err here. Okay? And let's take the error set of this polynomial, so this shaded region, and the error set is guaranteed to be a small subset of the hypercube, something like epsilon times 2 to the n. Okay? So the certifying polynomial that we'll construct is going to be kind of the product of this polynomial p with a polynomial q that's kind of just 0 on the error set. Okay? So what we do is we find a polynomial q of some small degree that's 0 on this error set. Okay? And again, in order to do this, we have to solve a system of linear equations. But note that the number of constraints now is much smaller than 2 to the n. It's only epsilon times 2 to the n. Right? So you started with a kind of very large number of constraints. Right? But now you're going to a different system which has a very small number of constraints. And now if you choose your parameter d2 carefully, it doesn't have to be very close to n by 2. It can be slightly far from n by 2. Then you'll have at least as many variables as linear constraints, and then you'll be able to find a non-trivial solution. Okay? So, and once you have this polynomial q and your original polynomial p, the final certifying polynomial is just the product of these two things. Okay, so it's q times p. So if you look at this polynomial, q is 0 everywhere here, right? P is 0 in this region. So the only place where this polynomial can be non-zero is right here, right? So this polynomial r being non-zero means that q is non-zero, which means the polynomial p is not making an error, and the polynomial p outputs 1, which means we are right here. Okay, and then now if you kind of just work out the parameters for this and set epsilon suitably, it's going to give you the right answer. Okay, so this is more or less how to construct a certifying polynomial for a Boolean function. You can actually also construct a certifying polynomial where the force set is small. So this is what we really need for the algorithm, right? We actually also need to say, we don't just need to say that the certifying polynomial is of low degree, we also need that the number of points where such polynomials are forced to be 0 here is small. Okay. In order to do this, you kind of just go through the same analysis, but you're a little more careful and you need an additional result. Okay. So again, what we want to do is start with our Razborov polynomial p and then multiply it with the polynomial q that's 0 on the error set. Okay. Right. But again, being 0 on the error set means that you're going to be 0 in a bunch of other places. Yeah, this is always the problem. You have a system of epsilon times 2 to the n constraints, but this might imply other constraints. You might get other constraints. Right? So a polynomial q is forced to be 0 here, but that forces it to be 0 in a bunch of other places. Okay? And all we need to say is that these bunch of other places is kind of small. Okay? That this set is small. Because once this set is small, in all the other places, q has a chance of being non-zero. So q times p has a chance of being non-zero. So the certifying polynomial has a chance of being non-zero. Okay. So the bad set whose cardinality we want to bound is really a subset of this set f prime, which is a set of points where q is forced to be 0. Okay. Right? And once you state the problem like this, it actually becomes a very neat algebraic problem. And it's actually been studied quite well in the literature. So let me just tell you what the solution to the problem is. So you have some set E. Yeah. So if you kind of lost track of the rest of the proof, this is actually a very neat statement that you can just take home from this talk. So you have some subset of f2 to the n of small size. Let's say epsilon times 2 to the n. Right. And what you want to know is you want to know what's the size of this set f prime. So the set f prime is defined as follows. All polynomials of some degree that vanish on E are also forced to vanish on the set of points in f prime. Yeah? So being 0 on E forces polynomials of this degree to be 0 on a bunch of other points. And how large is this set of points? Okay. Right? And this is a kind of very, very natural question. It's kind of a question about closure of polynomials and how large they can be. Right? But it's a kind of degree fixed kind of closure. Right? And it turns out this exact question has been studied in the mathematics literature, and we know exactly the bound. Okay, so this is a very recent result of two authors, Ni and Wang. Okay, but it actually also follows from some earlier results in the combinatorics literature. So which says the following, that the fraction of points in the hypercube that lie in f prime, right? So the fraction of points that are forced to 0, yeah, is at most the ratio of the number of constraints that we have to the number of variables, right? So E, the error set, the number of variables in our system of linear equations, right, yeah, right. So the number of monomials or the number of variables in our system of linear equations, right, is something like n choose at most d2. It's the number of coefficients of monomials of degree at most d2, right? And E is a system of constraints because we are forced to vanish on E. That's something we want, okay? And the number of consequences of the system of linear constraints, which is the cardinality of f prime, the fraction of that as a fraction of the entire space is less than or equal to the number of constraints divided by the number of variables, right? So if you choose your parameter suitably, you can ensure that the number of variables in your system of linear equations is much larger than epsilon times 2 to the n, right? Something like square root epsilon times 2 to the n. This forces your system not just to be kind of underdetermined, but very underdetermined. So you have many more variables than constraints. And in this setting, this result kind of says that the fraction of forced points is actually very small. Okay.
So just trying to pass this. So basically what you're saying is that if you choose D2, so you have k extra constraints,
right,
then you reduce f prime by a fraction k.
Not k times more constraints in some sense, yeah.
Okay.
Not just, yeah, it's not a, yeah, it's a ratio of the number of variables.
Okay. So if you choose k times more constraints, then you reduce it also by a fraction k.
Exactly, that's exactly right. So yeah, right. So if the number of variables, the number of coefficients is twice the number of constraints, the number of forced points is at most half the fraction of the entire space, yeah, and so on. Yeah? Okay, so it's a very neat result. So if you think about it, it's a kind of considerable extension of the kind of trivial result that says that if you have more variables and constraints, then you are not forced to be zero everywhere. You have a non-trivial solution.
So the trivial thing would have said that if you added if you added like 2 to the n 2 to the n over 10 constraints, you can reduce 2 to the n over 10 points. But then they said like, you only need to add like k times e constraints.
Exactly. That's right. That's exactly right. Right. Okay. So now, so once you have this result, it's more or less plug and play from the proof that I told you earlier. So you just choose your parameter d2 like this, and then your final certifying polynomial is q times p, where p is the Razborov polynomial. Okay, so that's more or less all I wanted to say. So so let me just summarize with a small list of open questions. Right. So so the compression algorithms that we have given here, so they're interesting, but they're so far the compression algorithms that we have kind of are in line with the circuit lower bounds that we already have. Okay, so can you come up with compression algorithms for other or stronger circuit classes? For example, even kind of reproducing Ryan's result for ECC0 with compression algorithms would be very interesting. Okay, and one kind of question I have, which is not quite in this line, but motivated by the proof of the theorem that we just saw, is the question of compression algorithms for this funny circuit class. So you take AC0 circuits, but you put a majority gate on top, or a threshold gate on top. Okay. And the reason this class is kind of interesting is that these certifying polynomials, or these one-sided error polynomials, were first investigated for lower bounds to do with this particular circuit class. So there's a circuit class for which we do know lower bounds, and they involve similar such polynomials, right? But I don't know how to mine that lower bound in some sense for a compression algorithm that comes up with some sort of computational problem that I don't know how to handle. Okay, so that's also an interesting question. And finally, I think this last result we saw on the previous slide, this result of Ni and Wang, is actually really interesting. It's a very natural problem for which we have a tight kind of inequality, and I would really like to see other applications of this result. Okay, so let me stop here. Thanks. Yes.
Result, like, does it use some deep machine learning?
No, it's actually quite simple. It's so it actually has to do with so it solves an extremal problem optimally, and the extremal problem is the following. So if you're looking at, let's say, some 2 to the r points in the hypercube, right? And you're looking at you fix some degree parameter d. What's the set of 2 to the r points that minimizes the dimension of the vector space of degree d polynomials restricted to these points? Right? So you can look at all degree d polynomials restricted to 2 to the r points. That's a vector space. What's the set of 2 to the r points that minimizes the dimension of the vector space? It turns out the answer is a subcube of that size. And that's it. So once you prove that, and the result, this can be proved. This has actually been proved at least, I think, in 3 places. Right? So once you plug that in, it's...
Other questions? Okay. So time for a short break. So let's thank Srikanth again.